Good morning, everybody. Sorry about the delay, but I had to get something for Dr. White's show and tell today. So let's get started. Good morning, Ruben. Good morning, everybody. Welcome to exciting morning of Chem 1105 with your host, me, Dr. White. I was going to open good morning, 1105 students, but that sounds too much like Good Morning, Vietnam. If you haven't seen that movie, you should. It's with Robin Williams. It's a great movie, funny movie, but a great movie. But anyways, today I will do some lecture and then we'll do the lab. And the lecture will help you with the lab. Remember, on Friday, I will go through the gas chapter 6 problem set. Make sure you do it before I do, so that way if you have any questions, you can ask. Remember, in my class, in my universe, there's no such thing as a dumb question. And by now you should all know I practiced that. All right, now, let me remind you, hand in today's lab. And also you have until tomorrow noon to hand in last week's lab. If you don't, you'll get zero, big 0 points. Hold on, let me really stress it. And hopefully you all get the hand in your labs or you'll get 0 points. They're easy points. Your final grade is based on points. And about a quarter of it is your labs. If you don't hand in your labs, you're not going to be happy with your final grade. I'm not going to be happy giving you that kind of grade. So hand in your labs. All right, let's get to work. Now, yesterday, I was talking about colloidal dispersions. And colloidal dispersions are small particles of one substance that are dispersed in another substance. And unlike solutions, and this is very important, colloidal dispersions disperse light so they can't, because of small particles, and they don't let light through. Solutions, because everything is dissolved, lets light through, doesn't disperse it. Now, am I lying to you? I don't know. Well, it's time to find out that your instructor, me, is a flashlight freak, and my best friend is even worse. Do I have flashlights? Yes, I do. Ooh, one more. No, I have about 25, 30. My best friend, he must have at least 50. All right, let's take a look. Assume there's sugar in here. You can see it's humid because it's cold water. And you can see the light come through. Let's go to a different color light. And green light, it's coming through. If I didn't have the cold water, there wouldn't be condensation. And just to have fun, red light. Blue and green, red and green, not for Christmas, it's for night vision. Now, I have a colloidal dispersion. And nothing comes through. It disperses light. It's red. It's not coming through. And different flashlight. Hopefully none of you are going like, oh, I can't see. But a colloidal dispersion like ketchup or some other things. Anybody need my ketchup if you got French fries? Oh, that was an awful, awful joke. Sorry. But anyways, colloidal dispersions are not really solutions. And you should know that colloidal dispersions disperse light. You should also know some examples of colloidal dispersion. Milk is an example of a colloidal dispersion. Latex paint, which is great if you've ever painted. It's a lot better than, easier to work with than the oil-based paints. And latex paints is an invention of a chemist. And that also is a colloidal dispersion. And finally, your blood. Your blood is not a solution, it's a colloidal dispersion. Dispersing medium is water, but in there you have many things, which I'm not going into, but do not try and shine light through your blood. Don't cut yourself, please. But you can try milk. Now, what is milk really? Have you ever thought about it? Well, milk is mainly water, and it has fat molecules and protein molecules in there, and might have some more things, but those are the main two dispersed media, or just, I always get those mixed up. Hold on. Dispersed phase. I always get medium and phase mixed up. But anyways, they're not truly dissolved in the water, but it's still the same throughout, homogeneous. And that's a colloidal dispersion. And you should know milk is an example, latex paint, and also blood. Ooh, coming up for Halloween. There's only 5 more shopping days till Halloween. Ooh. All right, let's move on. Uh-oh, I got hit by the dreaded dot virus. All right, now let's talk about solutions again. What if we were in a lab right now, face to face? I picked 2 volunteers and I said, why don't you make me a solution of salt and water? Or I could say, make a solution of sugar and water. And I'd have, here's some sugar, here's some water, here's some salt, here's some water, and make a solution. Well, would they be the same? No, they wouldn't even, you wouldn't taste anything in a lab, but if you were in your kitchen, oh, that tastes different from this one. Why? Because the amount of solute, the sugar or salt in the solvent water would be different amounts. So important thing is, how do you make sure a solution is always the same? Just like if you go to buy something like pop, how do you know they make things the same? Or in a chemical plant, if you have a solution you use in a chemical reaction, you don't want to, each time you make it, to be different. So how do you stop that? How do you make it the same? Chemists quantify. How do we quantify or quantitatively describe solutions? We use 3 different things. One is percent concentration, one is percent by volume, and the last one is molarity. Notice it's in red. By the way, if you haven't figured out, my favorite color is red. And when something's important, it's going to be in red. All right, let's talk about these different things. All right, listen up. Click percent concentration. I've turned off the switch. Will this be on a test or final? However, this is important for your daily life and something that could help you. So pay attention. So what is percent concentration? That's percent mass is equal to the mass of the solute in the solution times the mass of the whole solution, not the solvent, times 100. And this way, you can measure or weigh out certain percent concentrations. Remember, the mass of the solution is the mass of the solute and the solvent together. So the larger this number is, the more solute it is. Now, where do you see this? When you buy things. If you go to a local store and buy something, a lot of times the key ingredient will have percent of that ingredient. And the higher that percentage, the more that's in there. Now, where does that have use in your daily life? Well, let me tell you a story. When I first bought this house, first time I went out and mowed my lawn, I got attacked by every mosquito in northern Illinois. Oh, it wasn't fun. I said, I need some insect repellent. So I don't usually go. I go about 4 times a year, but I figured I needed it. So I went over to a big box store, this case, Walmart. So I went over where they had the insect repellents, and they had 2 different brands. One their brand, and another a big name brand. I think it was Off. And they had the Off was more expensive than the Walmart brand. And being a chemist who knows percent concentration, I looked at the labels. And the key ingredient called DEET, because I'm an organic chemist, I know that's the important thing. The Off had 2.2%. The DEET had 4.4%. Plus, the Walmart had a heavier bottle. Well, and it was cheaper. So what did I buy? Of course, the Walmart had twice as much of the key ingredient, which means it works better, and they give you more at a lower price. It's, as they say, a no-brainer. And guess what? I use my brains, so I bought the Walmart, and I still do. It works quite well. This summer when I was doing my lawn, no problem whatsoever, even though they're out in force. But that's how you use percent concentration. Another time, when I first bought this house, I had a crack in my foundation by the sump pump, and it was near winter, and it was just too cold to fix it. And a little water would leak through there if it's rained heavy or snowed and melted. And I could smell, oh, mold. So being an organic chemist, and I'll teach this later on, I knew, actually I have patents in this area, what molecules kill mold. And if you went to Walmart, again, it was one of my emergency trips to go, and they have a spray that allows you to kill mold. And there's a molecule called the quaternary ammonium salt, and that kills the mold. And they had a Clorox brand spray bottle and a Walmart brand. I looked and I saw the quaternary ammonium salt. Both were the same size spray can. And if you looked at it, the quaternary ammonium salt in the brand name was half of what it was in the Walmart, once again, to give you more, and the price was less. So why should I pay more for less of the key ingredient? But I know percent concentration. And when you see an ingredient percent, hold on a second. Maybe more than 1 second. Sorry about that. Couldn't find a label real quick. So anyways, look at the labels. Percent concentration is a way of chemical companies and other companies make sure their product is always consistent. And that way, the amount of solute, the active ingredient in a product, is kept constant. All right, now another way is called percent by volume. Again, click, the switch is off, but it's interesting. Percent by volume is the volume of the solute divided by the volume of the total solution times 100. The higher this is, the greater the solute is present in that solution. Now, the only place I really see percent volume, interesting enough, is on bottles of wine. Dr. White likes his white German wine because I worked in Germany and that's how I learned to love it. Pierce Porter, Golden Trocken, Cabernet, or Spätlese, Auslese. Outstanding. Ausgeschneidet. I pronounced that wrong. Anyways, percent volume, the higher the percent volume of the alcohol, the stronger it is. Now, that's not proof. Proof is another thing. And by the way, in hard liquor, proof was originally, you'd prove, was there alcohol in there enough that they weren't trying to sell you just a lot of water, and you'd burn it. That was the proof. And I'm not sure exactly how they got a number, but I do know if you take the proof of alcohol and divide it by 2, they'll give you the percent alcohol in a product. If you look at, how about vodka? It's about 80 proof, which means it's 40% alcohol by weight, not by volume. But wine has that. So that's another way of making sure a solution you make is consistent. The concentration, how much solute per solution is there. Now, the last one I want to talk about is molarity. Yes, it's important enough to get the whistle out. Molarity. And now, if I had a dial that went only to 10, how important this is, I've just turned it to 100. Yep, 100. And let's do this. Now, what is molarity? Well, molarity, which is shown by what's called capital M of a solution, is a ratio giving the number of moles. Yes, you know what a mole is, chemist counting unit of solute per liter of solution. This dot came here. It happens every once in a while. There it's gone. All right, molarity by definition, and notice I've got it in red, is moles of solute per 1 liter of solution. Molarity, moles of solute per 1 liter of solution. Wow, this must be really important because it says it on your screen, and it is. So molarity is defined as moles of solute per 1 liter of solution. Now, one of the things I haven't mentioned before, but I should mention now, 1 liter equals 1,000 milliliters. 1 liter equals 1,000 milliliters. Therefore, and I don't have it here, molarity, which is moles per liter, also, wow, where do these dots come from? That's gone. Anyways, molarity, moles per liter, is also defined as moles of solute per 1,000 milliliters. And this is the one you should know. Now, once again, and I've got to open something, so once, hang in there, or hold on, don't let go. All right, thumbs up, people. I haven't asked it all morning, so I'll ask it now. You see important information on your screen? Thank you. This will be for test number 3. And notice I have right here, so you don't have to memorize it, molarity, moles of solute per 1,000 milliliters of solution. Because mainly in a lab, we don't deal in liters, we deal in milliliters. It's easier to deal with and more accurate a lot of times. So again, molarity, moles of solute per 1,000 milliliters of solution. Now, when we talk about molarity, and I'm missing a slide here, oh no. So it's time to do instant slide. All right. Now, generally, you don't have to write the solution word down there. That's molarity. So let's look at molarity, important concept. So let me ask once more, thumbs up, people. Does everybody see what does this mean on your screen? Thank you, Nicholas. All right, what does this mean? Now, molarity is indicated by a capital M. So when I see 1.56 capital M, then a chemical formula, what does this mean? It means 1.56 moles of sodium chloride per 1,000 milliliters. You don't have to write the word solution. Again, capital M means molarity. And let's do another one. What does this mean? As soon as you see the capital M, you know that's molarity, and that's moles of solute per 1,000 milliliters. So what does this mean? 7.5 times 10 squared moles. Oops, I promise not the right. That's hard. Let me get something out of the way that you can't see, but I can. Moles and sodium hydroxide is a chemical. So its molarity, 7.5 times 10 squared moles of NaOH per 1,000 milliliters. All right, I'm going to let you try one. What does, let me fix my 8 there. I was going to do a 7, but I already did that, so I changed my mind. What does 8.134 capital M KBR mean? Your turn. And I'll do the poll. Don't forget to vote. All right, I think everybody's done, so let's do this. As soon as you see a number, capital M, and a chemical formula, that's molarity. And molarity is moles of solute, whatever that chemical is, per 1,000 milliliters of solution. So what does this mean? 8.134 moles of KBR per 1,000 milliliters of solution. All right, let's try something else. My first grade teacher would be so happy how well I'm printing. Hopefully you can read it. All right, let's look at the following 4 points each. What does this mean? And what is the solvent of this solution? And let's look at this. I'll do this one, then I'll let you try one. 4.37 capital M NaF sodium fluoride, bracket A, Q, close bracket. Well, what does this mean? Capital M, molarity, moles of solute, in this case, sodium fluoride. That's the active ingredient in your toothpaste that keeps your teeth healthy and your gums too, and per 1,000 milliliters of solution. But what is the solvent? And if you remember yesterday, AQ in brackets means aqueous solution, which means water is the solvent. Again, AQ in brackets means water is the solvent. And that's how you do that. I'm on a 7 roll. Let's try something different. And it's your turn. What does 9.31 capital M sugar bracket AQ close bracket mean? All right, I think everybody's done, so let's do this. Capital M, molarity, which is moles of solute per 1,000 milliliters of solution. You don't have to write down the word solution. So what does this mean? Capital M, molarity, there's 9.31 moles of sugar. Sugar is also known as sucrose. And yes, you can figure out how many moles of sugar there are. But this is molarity, 9.31 moles of sugar per 1,000 milliliters. And what is the solvent? Well, this tells you AQ is aqueous, and that means water is the solvent. Now, if you were to go into the storeroom for the chemistry department at COD, you would see a lot of bottles labeled with these types of labels. And they're called stock solutions. And stock solutions is where you make up a large amount of a certain molarity solution, because they're very useful to have. And you do that in chemical plants too. I've supervised making up molarity solutions where we made up 500 gallons. That's not a lot in a chemical plant, but think about it. You know the 55-gallon drums? Have you ever seen those big? Oh, hold on. Do I have time? I do. All right, does everybody see they don't show the cover on here? No, I don't want to stay connected. And these are reconditioned. I know I don't want to buy. Let's go here. If you notice, this is a 55-gallon drum. This has a lid on it. There are others. Let's see if here's what I'm looking for. If you look here, here's a 55-gallon drum. If you notice up here, there's one there, and you can't see the other one. Those are called, and I don't know how they got the name, bungholes. And these hold 55 gallons. And I've done where you make about 5 of these of solution, and you make them in a bigger container, and these are called totes. How they got that name, I don't know, but downstairs in my family room, I have a valve like this from a problem I solved. Once I solved it because it was caused by dirty totes, I took one of those valves home as a memory. And those are usually about 250 to 300. This is 330 gallons. And you make up stock solutions like that, and you can use them. Well, why do you make up stock solutions? Well, let's take a look. Now, in the lecture slides, I have important questions which we'll go through. And one of them is, how many moles in X milliliters of a known molar solution? So let's do this first. I promise not to write. That's ML. I hold on. Boy, this generation gap thing is awful. ML of and let's look at the following. How many moles HCl are in 451 milliliters of a 2.22 capital M HCl? And sometimes I'll even write in here solution. Sometimes I won't. So how do you do this? Well, you know the first thing, what are we trying to find? Moles of HCl. And what are we given? Well, we have 451 milliliters of that solution, and we're given this number with a letter and a chemical formula. And as soon as I see capital M, what do? I say, what does that mean? And I know capital M is molarity. That means 2.22 moles of HCl per 1,000 milliliters. And now I look, the only number I really have to work with is this. And if I had some sort of ratio, you know what's coming up. What units do I want my answer to be? This. And now, guess what time it is? You're right. It's time to use your good buddy. Ooh, I got to change the batteries there. Hold on. Your good buddy, your good friend, unit analysis. And how do we do that? Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And I'll write that in. And where do we get these numbers? From this, knowing that this really means this. So I have 2.22 moles per 1,000 milliliters. Now I should point out the 1,000 is an exact number. And now, before I pick up my calculator, milliliters divided by milliliters cancel out, because anything divided by itself equals number one, meaning it's gone. And I can pick up my calculator, turn it on first, clear it. And my calculator gives me this number. Ten to the 0 is 1. This is 3 significant figures. Yes, you got to use them. This is 3. Oh, he's in his rut again. And this needs to be 3 significant figures, because when you multiply and divide, don't forget the 1,000 is the exact number, plays no role in the calculation. And now, how do you round that off to 3 significant figures? I'll give you not 3, but 6 seconds. Go. Time's up. I gave you more than 6 seconds. Keep the 1, keep the 0, keep the 0. Use this to round off. Is 4 or less, I'll drop it. So the answer here would be 1.00 moles of HCl in that amount of the 2.22 molar HCl solution. Now hold on, I'll give you time in case, is everybody finished writing this down? Okay, I think you are. Remember, Dr. White has the fastest mouse wheel finger this side or the other side of the Mississippi River. So if I go too fast, always feel free to ask me to go back or say, wait, don't move yet. Now, here's the beauty of using, and it's beautiful and very useful, of molarity. All right, let me read this to you. How many milliliters of NaOH of a 6.54 capital M NaOH, and I could have written solution too, a lot of times I don't, are needed to get 2.61 moles of NaOH. So let's take a look at this. What are we being asked to find? Milliliters of NaOH solution. What are we given? We're given we need 2.61 moles NaOH, sodium hydroxide. And we're also given this number, 6.45, and then capital M, then a chemical formula, NaOH. Now, as soon as I see capital M, I know it's molarity, which is moles of solute per 1,000 milliliters of solution. So as soon as I see capital M like this, I'm going to say, what does that mean? And I'll remind myself that that means and that's what it means. So the only number I have to start with is really this. If I had some ratio, what answer do I want my units? What units do I want my answer to be? Well, that's milliliters of NaOH. That's ml. Tonight at midnight, I'm going to be giving cursive reading lessons. No, I won't. And now I'm going to use my good buddy, my good friend, unit analysis, whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And where do I get those numbers? But before I do that, I'm going to let the paper do my thinking and write those units down. This will help you on every test you ever take. let the paper do your thinking. And where do I get a relationship between milliliters of a solution and moles of a compound? Right here. We took the time to know that capital M is molarity, which really means this. And therefore, for every 1,000 milliliters that comes from here, there's 6.54 moles of sodium hydroxide. And before we do anything more, notice moles of sodium hydroxide divided by moles of sodium hydroxide. Anything divided by itself equals the number 1, and that cancels out. And now I can pick up my calculator, which I will, turn it on, clear it. And the number my calculator gives me, I'm laughing because here's what's on the screen. There are actually some more numbers. I'm not going to write it down. And I'm going to let you figure out on your own how many significant figures and write the right answer right here. Or just think about it. All right, time's up. This is 3 significant figures. Oh, he's in his rut again. This is an exact number. And this is 3 significant figures. Therefore, when you multiply and divide, the number you get has the same number of significant figures as the number with the lowest, which is 3. So round this off to 3, keep the 3, keep the 9, keep the 9. That's my 3 significant figures. I use the 0 to round off, and that's 4 or less. I drop that, and the correct number is . And the beauty of this is if I needed 2.61 moles of sodium hydroxide, instead of weighing it out and doing all sorts of things that take time, if I had a stock solution, I would only have to measure out 3.99 times 10 squared, which is 399 milliliters, and I would have those number of moles of sodium hydroxide. And that's why this is so useful. All right. Normally, when we lecture, we have 50 minutes. But when I go more than 50 minutes, like this morning, let's take a break, come back in 5 minutes. Let me look at my clock at 9:56, because Dr. White's going to get up and stretch. If we were face to face, I'd say, let's take a break. And I go sit down because I'd been standing for the last hour. I'll see you in 5 minutes, and we'll continue and do the lab. Let's get going. Everybody back? Give me a thumbs up if you're back. Oh no, a lot of people are not. All right, I see enough thumbs, so you're back. All right, let's continue on. Now, one of the things I should thank you, Alyssa, and everybody else who gave me a thumbs up. All right, one of the things I'm doing now is, which is uncharacteristic for me, is I'm rushing through some stuff. Not too fast, but still rushing through. In lecture tomorrow, I'm going to go back and we're going to go back over these types of molarity problems, but I want to cover enough for today's lab. Now, the question is, are you seeing having stock solutions, molar solutions is very useful. Well, how do you make up a stock solution? Well, you can't go to balance and weigh out moles or something. You have to convert, you weigh out grams, and then you can use that to make up molar solutions. Now, molar solutions, now for my problems, so you don't get messed up on significant figures, I could do it. I usually put unusual amounts, not exact amounts of volume. But when you're making up stock solutions in the lab, usually make either 100, 5, multiples of 5 or 10. And one of the most useful pieces of glassware is called the volumetric flask. Thumbs up, people. Can you see on your right part of your screen a picture with 4 what are called volumetric flasks? Thank you, Mackenzie. Now, if you notice each one of these, can you see my cursor? Give me a thumbs up if you can see my, looks like a little fan. You can see my cursor on your screen. Thank you, Alyssa. Thank you, Mackenzie. All right, you'll see a line right there. And when you fill this up to that line, and notice this says 250, that's exactly what the meniscus, where it's like a little U, the bottom of that U liquid is touching that line. That's exactly 250 milliliters. This is a larger one, and the line up here will give you 1,000 milliliters. And what you do is you weigh out your solute, like sodium hydroxide, put it in there, fill it up with water. Most of these are water, but you can use other solvents too. Put the top stopper back in, shake it, and dissolve it, and now you have that molar solution. Now, if you wonder if Dr. White's really a chemist, from my living room, I have a couch table, various glassware from my collection, which I got from eBay. You can get a lot of nice things on eBay. Oh, is this cute? And this is a 25 milliliter volumetric flask. See the line here. And does this say, usually these are within 0.03%, very accurate. And you put in the solute, then put in the water if that's the solvent, and you get it to this line. You put the little stopper in, and you go whoop, 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 whoop. You don't have to do the whoop, whoop part. And I have a glass bead in there because it looks cool. And These are volumetric flasks. Oh my goodness, 2 show and tell in one day. Are you lucky? But anyways, one of the important things is to figure out and I'm going to go through this again tomorrow in detail. And normally you use multiples of 5 or 10, but so you won't get messed up on significant figures. I won't. I did it again. All right, now if we look at this, let me read it. How many grams of NaOH are needed to make 247 milliliters of a 3.69 capital M NaOH solution? So what are we trying to find? Grams of NaOH. What are we given? 247 milliliters. And we're also given 3.69 capital M NaOH. And as soon as I see capital M, I know that's molarity. And remember, molarity equals moles solute per 1,000 milliliters. So immediately I know capital M. What does that mean? 3.69 moles of NaOH per 1,000 milliliters. Well, I didn't write it, almost did. And notice 10 points. Now, I have 247 milliliters, but there's no way I can go directly from that number to grams of NaOH. So what do? Well, first of all, you look at important information, test number 3. Almost said 2, we already had that. And notice here, molarity 2-step problem. Step 1, go milliliters to moles. That I just showed you. Step 2, go moles to grams. You should have learned that for test number 2. So let's go and do this. And again, notice I've cut down on the memorization. In the past, you would have to memorize that. But now I'm testing your knowledge of chemistry, not just your memory and your knowledge of chemistry. So we need 2 steps. And step 1, I did it again. Old habits are hard to break. Step 1, we go from milliliters to moles. So I have 247 milliliters of solution. I want to get to moles. And notice we're dealing with sodium hydroxide, so I'll put sodium hydroxide. And now how do I proceed in step one? I'll use my good buddy, my good friend, unit analysis. Moles go on top, milliliters go on the bottom of that ratio. And now I'm going to let the paper do my thinking, so I'll write this in. Oh, I didn't write it, I printed it. And where do I get these two numbers? From knowing molarity means 3.69 moles of sodium hydroxide per 1,000 milliliters. And now before I pick up my calculator, I will say, ooh, milliliters divided by milliliters cancels out, and I'm left with moles of sodium hydroxide. Clear my calculator, 245 times 3.69 divided by 1,000. And my calculator gives me this number. Now, this is a two-step problem. And again, as we talked about in the past, there's two methods of rounding off. One is round off at each step, and one is round off at the end. I'm an each step person, but for the test and the final, I will calculate both ways. So how do we round this off? This is he's in this three significant again. Three significant. Remember, the 1,000 is the exact number. Therefore, round this off to three significant figures. I'll give you 3 seconds, go. I gave you more than 3 seconds. Keep the 9, keep the 0, keep the 4. That's my three significant figures. This 0 is 4 or less. I'll drop that. And that's how many moles of NaOH. Are we done? No. We want to get the grams of NaOH. So now we need step number 2. Remember, this is in important information, test number 3. And now we have to do moles to grams. And now I'll come here. I'll have 9.04 times 10 to the minus 1 moles sodium hydroxide, NaOH. I want to go to grams of NaOH. And I'll use my good buddy, my good friend, unit analysis. Anybody keeping count how many times I've said that? I'm trying to go for the Guinness Book of World Record. And whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. I'll write it in. And where do I get a relationship between grams of a compound and moles of a compound? Well, in case you forgot, let's go to important information, test number 3. And notice I have moles of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. Yeah, it was in test 2, and you'll need it for test 3. So now that we know that 1 mole of a compound equals the molecular weight of compound, and the molecular weight of the compound is the sum of all atomic weights, I need the molecular weight of sodium hydroxide. And if you had your periodic table handy, Dr. White knows these by heart. Here's the sum of the atomic weights and check to make sure I did my math right. Oh, I did. And notice for addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest. 1, 1, 2. What's the lowest number? 1. Here's my decimal point. Keep the 0, use the 1 to round off, drop that as 40.0. So for every 1 mole, I have 40.0 grams of sodium hydroxide. And now notice moles of sodium hydroxide divided by moles equals 1. Why? Because anything divided by itself equals the number 1, cancels out. And now I can pick up my calculator and I have 9.04. Remember, use the minus sign here if you have to put it in again. And the number I get on my calculator whoop. Let's move us over here. And now I'll let you round this off to the right number. And if you guess that should be 3 significant figures, you're right, because this is 3 significant, this is 3. The 1 is the exact number, 3.61. Nope, the round off number is 5 or higher. So that drop this, oops. Drop that, increase this by 1, 3.62 times 10 to the 1 power grams NaOH. And the beauty of this is, if I want to make this molar solution and these many milliliters of that, I have to weigh out this amount of sodium hydroxide and add enough water to bring it up to this amount. Now, as I said, so we don't get into significant figure issues, I'll do that like that. And that's how you do this. Now, like I said, I rushed along on this, not too rushy, but still, I'll come back tomorrow and we'll revisit this. But I wanted to do that because it's time for your lab. Hold on, let's do this one. Let's get going. It's time for today's lab. Now, today's lab deals with molarity, and I just remembered I've got to download it. I also wanted to show you something. Switching to student view, also logging into Blackboard. And if we go to assignments, you'll see I have, everybody see, creating a solution of known molarity on your screen. Thank you, Ruben. All right. Now, notice right here, please note, you need to use the desktop version of Beyond Lab Z. There's instructions in the lab, and you can watch today's video, which I'll publish later today, how to do that in case you didn't do it. Now, let me do this. And here's one of the files. All right, now here's the molarity lab. And as it says, molarity is an important concept. It's defined as molarity, moles of solute per 1,000 milliliters of solute. And it's written as XM compound. And if you have 9.45 capital M NaCl bracket AQ closed bracket solution, then you have 9.45 moles of sodium chloride per milliliter, or that per liter of solution, and the AQ equals indicates solvent of the solution. In this lab, you'll be making solutions with two different solutes, and you'll be calculating the molarity of each lab. Now, this is conducted in a volumetric flask, and I have a link. Let's take a look at that link. I want to cheat you out of anything. If you notice, Wikipedia has some nice pictures of volumetric flasks, and you can take a look at that. And you also saw my, hold on, I do it again, my cute little volumetric flask. Now, this is a 25 milliliter. I've seen them as small as 5 milliliters. Are they cute? You know something? I'm going to have to look on eBay and get one of those. But anyways, here's a volumetric flask. And they're extremely accurate. They're usually accurate to 0.3%. That's like a 3,000ths of a milliliter accuracy, a lot of them. But unfortunately, Beyond Lab Z does not have volumetric flasks. I've talked to them about that, and they've done a little differently. And normally you won't do this in a real lab, but for this one, you'll do it in a graduated cylinder. Now, you'll be using the following key formulas. And this is similar to what I did, but different, sort of going the other direction. You're going to be calculating what is the molarity for a certain amount of solute. And there's two formulas. The moles of the solute are grams of the solute times 1 divided by the molecular weight of the solute. MW is molecular 1. That's formula 1. And the molarity, and this is a little different from what we did, but this you'll need for the lab, moles of solute, which you just calculated in formula 1, times 1,000 divided by the milliliters of solution. Now in this lab, that will be 50 milliliters. And here I have the procedure, but let's go to Beyond Lab Z. All right. All right. Now this is important. Thumbs up, people. Does everybody see Beyond Lab Z on your screen? Thank you, Mackenzie. Now, we're not going to use these here. At the end of the summer, Beyond Lab Z ported means changed over to HTML5, which is what you see here. But you see where it says web and desktop? We have to go to the old method because they still haven't ported over this lab to the web version. So you have to click on desktop. and we'll say this is what you're seeing. All right, see where it says chemistry legacy? Everybody see that? You have to go through this one. Thumbs up, people. Can you see on your screen chemistry legacy? Thank you. Click on that. Make sure you click on open. All right, does everybody see welcome to Virtual Chem Lab? And at the top, it says titration calorimetry. Thank you, Gabby. All right, now here's, pay attention. It's in the procedure, but watch. See where it says worksheets, the left lower part of the screen. Click on reactions and stoichiometry. Big word, it's called stoichiometry. So everybody see how I expanded that? Thumbs up, people. Thank you, Ruben. Now, this bar here, you'll scroll down and see where you have two creating solutions of known molarity. If I highlight the top one, if you look in the center of your screen, it says weigh a sample of baking soda, sodium bicarbonate, and create a solution of that known molarity. If you go to the, I did the second one. If you do the top one, says weigh a sample of ammonium chloride and create a solution of known molarity. These two, you'll do both of them. Let's click on the top one first, creating a solution of known molarity where it says in the center for ammonium chloride. I've mouse clicked. This, and let me make sure you're seeing that. Does everybody see the lab with, this is called a burette and a yellow balance or yellow, yeah, yellow balance. Thank you. Now, click on the, first of all, where the drawer says beakers, click on that. Ooh, sound. And take a beaker with your left mouse click and put it on the lighted circle by this brown jar, which says ammonium chloride. Now, if we were face to face, I would be telling you, close your drawers. It hurts if you walk into them. I just did. Now, click on the balance. Now, over here, here's our ammonium chloride. Take the lid off by clicking on it. And now, take some, this is called weighing paper. You'll put it on the balance, then you'll share it. That's zeroing it. And it's 0. And it might bounce around a little. This isn't. Now, here's the neat thing. Here's a spatula to get the solid out. How do you get that? You click on the bottom picture, and notice my spatula is now full. And now you have to put your cursor right by the corner of the filter paper and you dump it in. Notice the amount has increased. And this is going to bounce around because in good balances, people walking by, their vibration or their footsteps can move this around. Now you're going to want to take 2 spatulafuls. So we'll take a second one. Again, put your spatula. If you don't have it aligned right, this will just kick out. And now you want to write down 1.9835 or 36, whatever. If it bounces around, pick one of the numbers, and it doesn't matter. And notice this is 2, 4, 5 significant figures. And write that down in table. I'll show you where. Now you take the filter paper, hold it over the beaker, and let it go. And now we're going to exit, zoom out. And now this first graduated cylinder, see where it says in the upper right, 50 milliliters empty. When I hold it over there, you're going to take the beaker, left mouse click, hold it over there, let go. Now that's bad sound effects because the solid isn't going to sound like a liquid. And now we're going to take this. Before I do this, let me teach you something. You notice here, they have a tap that's curved with the white tip. This is deionized water. The other tap with the two handles is regular water, as I call it, from industry city water. The deionized water, ions have been taken out of that, and it's pure. We'll take this, move it under there. When the water starts, that's it. And you're done with that lab. Now, let's look at something first. Remember the weight I had? You'll put the weight here, 1.9, whatever it was, for ammonium chloride. I give you the chemical formula. The volume of the cylinder is 50. I didn't put it in there, but these are both 50 milliliters. You put the weight here, then you use Formula 1. I made it real easy for you, and calculate the moles of solute, and you'll use that number in Formula 2 to calculate the molarity right here. Yeah, I don't like the way that looks. You'll do the molarity right there. And that's the first part. Now, the second part, again, under worksheet, you'll do the second creating molarity, and notice it says sample of baking powder. If you go ahead, and I'm doing it again, and you'll do the same thing, take a beaker, go here, close the drawer, zoom in on this, and notice now when I put this by the bottle, it says baking soda. And you'll unscrew the cap, put the weighing paper on here, tear it, click on this, dump it, do a second one, dump it, and then you'll record this number, and you go over and, well, first of all, and you'll take and pour this into the graduated cylinder. I might as well do it. Take this, and I filled it up. Well, let's make sure. Now it's full. And that's the second part. And then for the baking powder, I'll put the number in there. This is still 50. I'll do Formula 1 to calculate the moles, in this case, of baking powder. And then I'll do Formula 2 and calculate the molarity of that solution. Now, the important part of this lab are the questions. And I give you more practice using Formula 1 and Formula 2. And that's today's lab. If I look at the clock, we're done. You get to get out early. And with that, I'll say, gang gesund, be healthy, bye now. Don't forget, still wear your mask. If you haven't gotten your shots yet, you should. And I'll see you tomorrow. If anybody has any questions, I will, thank you, Ruben. I will stick around for a couple minutes. Other than that, you can walk or run away or log off quickly. Bye now.